In today's lesson, we're going to talk about incomplete quadratics and the special ways we have to solve them. So first off, how to recognize an incomplete quadratic. Basically, any quadratic that is missing the x term. So the bx terms, 5x, 3x, whatever, there's no x term. We just have something with the x squared, and then we have a constant. That is an incomplete quadratic. These types of equations can sometimes be solved using the zero product law and difference of perfect squares factoring. So because we can solve some of those like that, and we've already done difference of perfect squares, we're going to remind ourselves of that method and then move on to some other ways to solve them. So with difference of perfect squares and any zero product law factoring or zero product law method for solving quadratics, the first thing we're going to do is set the equation equal to 0 and then factor it. So we see that we have difference of perfect squares. We can see this is an incomplete quadratic because it just has something with x squared and a constant, and there's no x term. And we know it factors into x plus 4, x minus 4. So then for our solutions, we get -4 and +4. In the second problem, once again, we're using the zero product property, and then they're telling me that the type of factoring is going to be difference of perfect squares. Quickly with this one, I see 5 isn't a perfect square, but I can take that out as a GCF. So I have 5 times x plus 2, x minus 2. The 5 equals 0 doesn't make sense, so that's gone. So I get -2 and +2 as my answers. Now it says because they lack the bx term, incomplete quadratics can also be solved by isolating the x squared term and taking the square root of both sides of the equation. So instead of factoring, I can notice that in the first one, I'm actually set up and ready to go, and I can just take the square root of both sides of the equation. Now, initially, this looks like if I take, this cancels the squared, that's why it works, and the square root of 16 is 4. But I'm actually looking for all numbers when squared that give me 16. So 4 squared is 16. But -4 squared is also 16, and I don't want to lose that answer. And I can also see when I factored that -4 was an answer. So when we use this method, when we take square roots to solve equations, we always, when we do that, need the positive or negative value of that square root. So this is plus or minus 4. This is the same thing as saying x equals -4 and x equals +4. So looking at the next one, if we're using this method of incomplete quadratics, if we're isolating the x squared, first thing I would do is move over the 8. And then I would divide by 5. I want to have the x squared by itself before I take the square root. And then I take the square root. Initially, maybe I only remember the +2, but when I take this square root, I need both positive and -2 as the answers. So in any of these problems, we can also write these two answers in our set notation brackets. That's fine as well. Now, before moving on, I just want to point out that the reason that we haven't used this method so far with quadratics is because with something that's not complete. So if I had x squared, let's say -5x equals 6. There's no way to get the x squared by itself. Like I've seen people try to do this. Okay, so I guess I shouldn't say it that way. There is a way to get the x squared by itself, but then when I take a square root, that doesn't do anything for me in terms of solving the equation. So whenever I have this x, there's really no point to try to use the method of square roots. So anyway, don't do this. Remember, this only works when that bx term is missing, okay? Now, right now, this just looks like a different way to do something. So I could use difference of perfect squares. I could use isolating and taking a square root. But actually, it's a method that works even when difference of perfect squares doesn't. So if I took this problem, and just watch this, if I set this equal to 0, I can't factor it because 7 isn't a perfect square. But the method of incomplete quadratics will work. So let me just erase this. So with the method of incomplete quadratics, the first thing I would do is take the square root of both sides. And I get x equals the square root of 7. And specifically, I need to think about the positive square root of 7 and the negative square root of 7. So my two answers are negative square root of 7 and positive square root of 7. So we can see here we do get an irrational answer. And those will start to pop up here and there in the next few lessons, even heading towards something that's even a little bit more complicated than that. So also when I see that I get these square roots in my answer, that's also a key that I probably couldn't have used factoring, and I would need this method to solve them. So let's look at the next one. I could set it equal to 0. It's another one that doesn't factor, but we are isolating and taking a square root. Anyway, so I have 3x squared equals 24. Divide by 3. And then take the square root of both sides. Now, unlike the first one up on here, where we could take the square root and get a nice integer, 4, or this one where we took the square root and we had to stop there, square root of 7 doesn't simplify. The square root of 8 is not a perfect square, 8 is not a perfect square, but it has a perfect square in it. So this should look familiar from geometry. But we want to break this up into the biggest perfect square that goes into 8, which is 4, and whatever it's multiplied by, which is 2. So I'm writing something equivalent. 8 is 4 times 2, and I'm allowed to break up square roots that way. I'm still going to put the plus or minus in the front because that's what I do when I'm solving these problems. Basically, when you have x squared, we get 2 answers. So here, my final answer, I take the square root of 4, which is 2. And then the second 2 has to stay inside because I can't take the square root of 2. So we're going to practice more on techniques for simplifying square roots on the next page. But my two answers to this one are negative 2 square roots of 2 and positive 2 square roots of 2.